Hello students, welcome to chemistry class. Today, let us learn the lesson periodic classification of elements. We have learned in the previous class about the classification of elements. First classification was done by the scientist Doberener's law of triads, which states that when the elements are arranged in the increasing order of atomic masses in a group of three, the atomic mass of the middle element was found to be roughly the average of the atomic masses of the other two elements. What are its limitations? Doberener could identify only three triads from the elements known at that time. Next comes Newland's classification. We have learned Newland's law of octaves, which states that when the elements are arranged in the increasing order of the atomic masses, the properties of the eighth element are a kind of repetition of the first. It also has some limitations. The first point is that Newland, it was found that the law of octaves was applicable only up to calcium. After calcium, the eighth element did not possess the properties similar to that of the first. Second point, Newlands assumed that only 56 elements existed in nature and no more elements would be discovered in future. Third point, to fit the elements into his table, Newlands not only adjusted two elements in the same slot but also put some unlike elements under the same note. So the next classification was done by Mendeleev. He classified the elements based on two fundamental properties: atomic mass and similarity in properties. He stated one law. Let us see what is Mendeleev's periodic law. It states that the properties of elements are the periodic functions of their atomic masses. Next, we learned achievements of Mendeleev's periodic table. The points are: the first point, Mendeleev could classify almost all elements in his periodic table. Second one, he left some gaps for some undiscovered elements and predicted their properties also. When these elements were discovered later, they had the properties that Mendeleev had predicted already. Today we are going to learn the topics: limitations of Mendeleev's classification, modern periodic table, and the positions of elements in the modern periodic table. Let us see what are the limitations of Mendeleev's classification. The first point, Mendeleev could not assign a correct position to hydrogen in his table because the properties of hydrogen resemble that of both alkali metals as well as halogens. What are alkali metals? Lithium, sodium, potassium, etc. These metals are called alkali metals. Hydrogen and alkali metals have similar electronic configuration. You know, hydrogen's atomic number is 1. It is having only one shell, K shell, with one electron. Let us take one of the example of alkali metals, sodium. Its atomic number is 11. Electronic configuration 2 in the K shell. In the L shell there are 8 electrons and M shell 1 electron. That is, in the outermost shell there is 1 electron. So as both hydrogen and alkali metals have same number of valence electron, that is 1, both have similar properties. So like alkali metals, hydrogen also combined with halogens, oxygen, and sulfur to form compounds. Halogen means the group of elements fluorine, chlorine, bromine, iodine, etc. These are called halogens. So let us see. Hydrogen form compound with one of the halogen chlorine. The formula of the compound is HCl, hydrogen chloride. When alkali metal, one of the alkali metal sodium form a compound with the chlorine, it also has the similar formula NaCl. When hydrogen combine with oxygen, the compound formula is H2O, water. When alkali metal, that means sodium combined with oxygen, it also has a similar formula Na2O, H2O, Na2O. Hydrogen with sulfur, the formula of the compound is H2S. Alkali metal with sulfur, its formula is Na2S. So, hydrogen and alkali metal, when both combine with halogen, oxygen and sulfur, the compounds are having similar formula. Now let us see what is the similarity of hydrogen with halogens. You know these halogens are diatomic molecules. Fluorine molecule we can write it as F2, chlorine Cl2, bromine Br2 and I2, iodine I2. Hydrogen also form a diatomic molecule H2. This is a similarity of halogen with hydrogen. So as hydrogen resemble both alkali metals and halogens, where to place this hydrogen in the periodic table, whether along with the alkali metals or along with the halogens. So Mendeleev could not assign a correct position to hydrogen in his periodic table. This is one of the limitation. Let us see the other limitation. The isotopes of the same element will have to be given different positions if atomic mass is taken as the basis. This would disturb the symmetry of the periodic table. What do you mean by an isotope? You have learned in 9th standard. Isotopes are the atoms of different atoms of the same element with different mass numbers, different atomic masses. For example, you have studied carbon. There are 3 isotopes, carbon 12 with the mass number 12, with the mass number 13 and with the mass number 14. Same element. So, in his periodic table, Mendeleev arranged the elements in the increasing order of their atomic masses. So, carbon 12 should have been given one position, carbon 13 other position and carbon 14 other position. That means same element should have been given different positions. This disturbs the symmetry of the periodic table. Next point is that we have already seen that while classifying the elements in his periodic table, Mendeleev left some gaps in between some elements. So as the atomic masses do not increase in a regular manner in going from one element to the next, it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements. That means the atomic mass was not increasing in a regular manner. So in between two elements, how many elements will be discovered, he could not predict. So once again, the limitations of Mendeleev's classification are: one point it is, he could not assign a correct position to hydrogen in his table because hydrogen resembles both alkali metals as well as halogens. Another one, the problem of isotopes. The isotopes of the same element will have to be given different positions if atomic mass is taken as the basis, but this would disturb the symmetry of the periodic table. One more point, the atomic masses do not increase in a regular manner in going from one element to the next. So it was not possible to predict how many elements could be discovered between two elements. This is especially in the case of heavier elements. Let us learn the next classification. In 1913, Henry Moseley showed that the atomic number of an element is a more fundamental property than its atomic mass. Accordingly, Mendeleev's periodic law was modified and atomic number was adopted as the basis of modern periodic table. Let us see the modern periodic law. Modern periodic law can be stated as properties of elements are a periodic function of their atomic number. So we have seen in the earlier classifications, Dobereiner's classification, Newland's and Mendeleev's. All these classification elements were arranged in the increasing order of their atomic masses. So if atomic number can be taken as a basic property was suggested by the scientist Henry Moseley, and he modified Mendeleev's periodic law. We can state the modern periodic law as properties of elements are a periodic function of their atomic number. What does it mean? When the elements are arranged in the increasing order of their atomic number, one element after a regular interval repeats the property of the other one. So what is meant by atomic number? You have learned that atomic number is the number of protons in the nucleus of an atom. It is also equal to the number of electrons in the shells. It increases by 1 in going from one element to the next. You have learned last year, the first element is hydrogen, its atomic number is 1. Next element helium, atomic number 2. Next lithium, atomic number 3. That means while going from one element to the other, atomic number increases by 1. Elements, when arranged in order of increasing atomic number, lead us to the classification known as the modern periodic table. Prediction of properties of elements could be made with more precision when the elements were arranged on the basis of increasing atomic number, because the property of an element depends upon its number of electrons or how the electrons are arranged in different shells. That means it depends upon the atomic number. Let us see the positions of elements in the modern periodic table. So this is modern periodic table. Here you can see some horizontal rows and vertical columns. How many vertical columns are there? We can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. There are 18 vertical columns in the modern periodic table. These vertical columns are called groups. Let us see how many horizontal rows are there in the modern periodic table. 1 row, 2, 3, 4, 5, 6, 7. You can see here 2 more rows, but these are the part of the 6th and 7th rows. These horizontal rows in the periodic table are called periods. So, this row, which is a part of the 6th period, and this is the part of the 7th period. We are not going to learn about this lanthanide series and actinide series, which is known as lanthanide series and actinide series. We are not going to learn about them in standard 10th. We are also not going to learn about the 3rd to 12 groups. We are learning only about first group, second group, 13th group, 13th to 18th group in standard 10th. So as we have seen, the vertical columns in a periodic table are called groups and the horizontal rows in a periodic table are called periods. In the modern periodic table, there are 18 groups and 7 periods. Next, we are going to learn the positions of elements in the modern periodic table. So regarding this, you have to remember 2 points. The elements present in any one group have the same number of valence electrons. Valence electron means electrons in the outermost shell. Atoms of different elements with the same number of occupied shells. The next point is atoms of different elements with the same number of occupied shells are placed in the same period. So let us see the first point. The elements present in any one group have the same number of valence electrons. To understand this, let us consider some examples. Let us take Group 1 elements. These are also called alkali metals. Lithium, sodium, potassium, rubidium, cesium and francium. As hydrogen resemble both with alkali metals and halogens, already we have seen there is an anomaly in its position. So lithium, sodium, potassium, rubidium, cesium and francium are the first group elements. Let us write the electronic configurations of 2 or 3 elements in this group. So lithium, its atomic number is 3. How can we write the electronic configuration? In the K shell, there are 2 electrons, L shell, 1 electron. Next, sodium, atomic number is 11. Electronic configuration, K shell 2, L shell 8 and M shell 1. Potassium, its electronic configuration is 2881. All these elements, we can see that in the outermost shell, lithium, the outermost shell is L shell, there is 1 electron. For sodium, the outermost shell is M shell, there is 1 electron. Potassium also in the outermost shell, there is only 1 electron. So all the elements in the first group have 1 electron in the outermost shell. That means group number and the number of valence electrons are same. Or we can say the elements present in any one group, here the group is first group, have the same number of valence electron. Here all these elements have 1 electron in the valence shell. Let us take another example, group 2 elements. They are also called alkaline earth metals. They are beryllium, magnesium, calcium, strontium, barium and radium. Let us write the electronic configuration of 2 or 3 elements in this group. Beryllium, atomic number 4, electronic configuration 2, 2. Magnesium, atomic number is 12, electronic configuration K shell 2, L shell 8 and M shell 2. For calcium, atomic number 20, electronic configuration 2882. We can see all these 3 are having same number of valence electrons. How many? 2. In the outermost shell, there are 2 electrons. We can generalize this. That means second group, all the elements have 2 valence electrons. That means elements belong to second group. All the elements belong to second group have same number of valence electron, that is 2 electrons. Next, let us consider group 17 elements. They are also called halogens. They are fluorine, chlorine, bromine, iodine and astatine. Let us write the electronic configurations. Fluorine, atomic number 9, electronic configuration 2, 7. Chlorine, atomic number is 17, its electronic configuration K shell 2, L shell 8 and M shell 7. How many electrons in the valence shell of fluorine? 7. For chlorine, 7. That means all these elements have same number of valence electrons. That means 7 valence electron. So group 17, all the elements are having same number of valence electron. Or we can generalize, the elements belong to the same group have same number of valence electrons. The elements present in any one group have the same The elements present in any one group have the same number of valence electrons, or we can say groups in the periodic table signify an identical outer shell electronic configuration. For example, all the elements in the first group have same number of electron in the outermost shell, that is one valence electron. All the elements in the second group have same number of electrons in the outermost shell, that is 2 valence electrons. All the elements in the 17th group have the same number of electrons in the outermost shell, that is 7 valence electrons. So let us see the relation between number of valence electrons and group number. First group, all the elements have 1 valence electron. Second group, all the elements have 2 valence electron. As I have told, we are not going to learn about 3 to 12th group in standard 10th. Next, we'll see 13th group, all the elements have 3 valence electrons. 14th group, all the elements have 4 electrons in the outermost shell. If the valence electron number is 5, that element belongs to group number 15. 16th group, all the elements have 6 valence electron. Or we can say if there are 7 valence electron for an element, it belongs to group 17. 18 groups, all the elements have 8 valence electrons. Same number of valence electrons, that means 8. Next, the second point we are going to discuss now, atoms of different elements with the same number of occupied shells are placed in the same period. To understand this, let us consider second period in the periodic table. Let us see the elements. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So let us see the electronic configuration of these elements. Lithium, atomic number 3. What is the electronic configuration? K shell 2, L shell 1. For beryllium, atomic number is 4. Its electronic configuration is 2, 2. Boron, atomic number 5. Electronic configuration 2, 3. For carbon, atomic number 6. Electronic configuration 2, 4. Nitrogen 2, 5. Oxygen 2, 6. Fluorine 2, 7. And neon 2, 8. So, how many shells in which the electron occupy for all these elements? All these elements, the electrons are filled in 2 shells, K and L shells. So, we can see in period 2, all the elements, the number of occupied shell is also 2. That means period number is equal to number of occupied shells. Let us consider the period 3, elements in period 3. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Let us see their electronic configurations. Sodium, atomic number 11, electronic configuration K shell 2, L shell 8, M shell 1. For magnesium, it is 282. Aluminium, 283. Silicon, 284. Phosphorus, silicon, atomic number is 14, electronic configuration 284. Phosphorus, atomic number 15, electronic configuration 285. For sulfur, 286, chlorine 287 and argon 288. So, how many shells is filled with electrons? 3 shells. So, number of occupied shells are 3, period number also 3 here. So, we can generalize that period number is also equal to number of occupied shells. So, once again, let us see the points regarding the position of elements in the periodic table. The elements present in any one group have the same number of valence electrons. Period number is equal to number of occupied shells. That means Atoms of different elements with the same number of occupied shells are placed in the same period. If there are 4 occupied shells, that element belongs to 4th period. For an element, electrons are filled in 6 shells. The element belongs to 6th period. If there are 2 shells, the element is in 2nd period. So you have to remember these 2 points in mind. Based on this, we are going to discuss some questions in the next class. Today, we have learned the topics: limitations of Mendeleev's classification, modern periodic table, and positions of elements in the modern periodic table. Hope you understood today's class. Thank you, children.